I'll start green. Okay, let's see. Okay, just make sure the sharing screen is working.
Yep.
Cool, good. Okay, so I'm gonna start off by just recapping the very end of yesterday's lecture. Yesterday we talked about this spectral form factor very briefly. You take two copies of the thermal partition function, and you analytically continue beta to beta plus IT and beta to beta minus IT. And this quantity, the spectral form factor, is like a auxiliary quantity for studying the level statistics. It depends on pairs of energies, and in particular has these phases that are proportional to the energy differences. So we asked, what does this thing look like, spectral form factor, if you average over it? You average over the ensemble of GUE Hamiltonians. And we found this structure, this slope, ramp, and plateau. And the ramp and plateau come from the sine kernel contribution to the pair correlation function. Where the ramp is something a little bit simple in terms of this pair correlation function. It's the perturbative piece of the sine kernel where you average out the oscillations. But the plateau comes from these rapid oscillations. So in terms of the matrix, the integral over GUE Hamiltonians, the ramp is something that's easier to see. It's perturbative in 1 over L. The plateau is something that's non-perturbative in 1 over L. And so real quick, I'm going to say, okay, our goal for today is going to be to try to see how to calculate the spectral form factor in gravity and find signatures of these ramps and plateaus. So gravity, we usually think of as, in ADS-CFT, we usually have a definite Hamiltonian. We're not averaging over random Hamiltonians. And so what we might expect to get out of gravity is something that looks like the spectral form factor for a typical draw of a Hamiltonian from the GUE ensemble, for example. This will just be a toy model for our expectations. So we can ask, what does the spectral form factor look like for a fixed Hamiltonian, typical one of order 1 probability in the GUE ensemble? So you can plot it in Mathematica, and that's some homework if you guys are interested. Mathematica is a nice way of generating GUE Hamiltonians. And we find this sort of picture. Here I've drawn it so that it's like a log-log block. You start out at this large value, order L squared, and you decay. But when you start to get to where the average ramp would be, you find a very noisy signal. So the red signal is the function for a fixed Hamiltonian. The black line underneath is the ensemble average. So we can see the signal is noisy and oscillates erratically around the average ramp, and then erratically around the average plateau. So for a fixed Hamiltonian, you don't see the ramp and plateau exactly. You see a big noisy function, and in fact, the size of the noise is the same size as the signal itself. So if down here we can say the ramp is of order 1. And that means the oscillations are also size of order 1. Over here, the ramp has gotten to size of order L, and the size of the oscillations is of order L around it. So the oscillations are big, and so in some sense, the ramp and the plateau are a bad approximation to the spectral form factor for a specific choice of Hamiltonian. So if we are considering a fixed Hamiltonian without averaging, is there any sense in which the ramp and plateau are meaningful? So I just want to emphasize that we can indeed make them meaningful by not averaging over an ensemble of Hamiltonians, but taking a fixed Hamiltonian and averaging the spectral form factor, for example, over time windows or in some other way. So if we take this noisy signal and we say we average over a little time window here, average over a little time window here, and here, and here, and here, we expect that, and we can show that in some cases, the noise should average out, leaving behind this ramp. And so maybe in other systems, there's additional ways to average So you take a fixed system and you can average over time. Maybe you can average over some coupling constants or something like that. But there's various ways for even a fixed system to average out the noise in the spectral form factor and find this ramp in a plateau. So we think these should be there in some sense, even for fixed Hamiltonian systems. So let's keep that in the back of our mind as we're trying to study spectral form factor in gravity. So one note about our new perspective of trying to do this in gravity is that these perturbative 1 over L effects that describe the ramp in the random matrix theory are non-perturbative effects in gravity. That's because our perturbation theory in the random matrix theory was in 1 over the size of the Hilbert space, which is L. But in gravity, the size of the Hilbert space is like e to the s, where s, the entropy of a black hole, is 1 over g Newton. So ordinarily we do perturbation theory in g Newton, but these effects that we're looking for that are 1 over L are exponentially small in g Newton. So that is going to make these effects a little bit more novel. Okay, so now we're going to get to, well, I've written the title up top, the ramp from a wormhole. That's a bit of a heads up for what's going to come later. But what we're going to start with is just try to calculate a partition function in gravity. So the spectral form factor is 2 copies of the partition function, analytically continued. So to get started, let's just calculate the partition function, C of beta. So in regular quantum mechanics, the partition function trace e to the minus beta h can be written as a path integral, periodic in Euclidean time. So Euclidean time tau is periodic in beta. Beta is the inverse temperature. So in ADS-C of t, what this means is that you fix the metric on the asymptotic boundary to be periodic in Euclidean time. And because the boundary has infinite length, what we want to do is fix a renormalized version of the length, and we'll see some detail about that in a moment. So here I've drawn a picture of an example geometry that contributes to the partition function in ADS-C of t. So out at the boundary, the geometry is asymptotically Euclidean ADS with period in Euclidean time beta. But inside, we integrate over all geometries that have these asymptotic boundary conditions. So here the picture is for like 2D gravity, because I can't draw a higher dimensional version of this. So ordinarily, when we try to study the partition function in gravity, it's dominated by a classical solution. And for sufficiently high temperatures above the Hawking-Page transition, it's dominated by the Euclidean black hole. So we're interested in studying black holes, so we're going to restrict our attention to these high temperatures where this black hole solution should dominate. And so then we can compute the partition function. We just find this classical solution, the Euclidean black hole, take its action, maybe consider some perturbative fluctuations around it, and we get a function z of beta, which we can then attempt to continue with beta going to beta plus it. And then this might be a contribution to the spectral form factor, where we take that and take its modulus squared. But the problem is that we're interested in studying these very long times. We would take t to be something like maybe even proportional to L or something like that. So this would be exponentially long times in gravity. So if we're taking this function, which we computed perturbatively from the saddle point, and then continuing it to these very, very, very long times, we may lose control over the perturbation series. Maybe that there's large perturbative corrections that we can't really calculate because they depend on time, and time is becoming very large. So in general, it's difficult to have a nice control over this function computed in this way from the black hole saddle point. What we're going to do now is we're going to restrict our attention to a nice simple model of gravity, JT or Jakob-Teitelboim gravity, because in this case we have control. So this JT gravity is going to be basically our main model that we're going to study for today's lecture and tomorrow's lecture. It's very simple, and we can say a lot about it, and it's got some interesting, surprising facts about it. So here I'm going to give you a bit of an introduction to JT gravity. It's a two-dimensional theory of dilaton gravity. So we have a metric, g mu nu, and we have a dilaton phi. The cosmological constant is negative in this model, and we set it to -2. Turns out to be a simple choice. So you can think of this model, JT gravity, as part of the dimensional reduction of a near extremal four-dimensional black hole. The near horizon geometry of one of these higher dimensional near extremal black holes looks like ADS2. So this JT gravity is a theory of ADS2 gravity. In that case, so this higher dimensional geometry, this four-dimensional black hole has a two-sphere, and in the dimensional reduction of JT gravity, the size of this two-sphere is related to the dilaton. So the size of the two-sphere is like this phi, call it sub dr for dimensional reduction. It's equal to a large value phi naught plus phi, which is the field we integrate over. And so in the higher dimensions, the area of this two-sphere at the horizon is the entropy of the black hole. So in JT gravity, we think of the entropy as phi naught, this large value, plus the value of our fluctuating phi at the horizon. So this is just a way to think about JT gravity, to connect it to sort of more conventional higher dimensional gravity. But what we're going to do is we're going to take this theory at face value, just 2D gravity, forget about the dimensional reduction, and we're going to work with it on its own. And so I've written here the Euclidean action for JT gravity as a sum of 3 terms. So we're going to talk about each term one by one. They each have an important role. So the first term here, we can see the appearance of just the normal Einstein-Hilbert term in the action. And we have an analogous boundary term. So this is a little bit messy, but this is the boundary of the manifold and extrinsic curvature. So in 2 dimensions, this Einstein term is trivial. It's just topological. So altogether, this term is just proportional to the Euler character of the manifold which you're evaluating the action on. And we've given this Euler character term coefficient S naught. S naught is like the phi naught I mentioned in the previous slide. So S naught is a large number that's going to be part of the entropy of the system. So the second term here, we have a term which is the dilaton multiplying R plus 2. So this would be the cosmological constant. And so we can see that if we vary phi to get some equations of motion, we find the equation of motion R plus 2 equals 0.
Can I ask a question?
Mm-hmm.
This S naught is the entropy of the 4-dimensional black hole, right?
Yeah.
But it's not the entropy of the 2-dimensional system that you're considering. So
we will find that it contributes to the entropy also, yeah. But this is the way to think about that is the right way to think about it in terms of the dimensional reduction.
okay, thanks.
Mm-hmm. So this term here will allow us to focus only on constant negative curvature metrics. And those are simple, they're just pieces of Euclidean ADS2, which is just pieces of hyperbolic space. We'll talk more about that in a moment. So finally, the last term here gives an action for the boundary. So because we're computing a partition function, we have an asymptotic boundary, and we have to regularize it. This will give some action for that boundary. And so this is actually somewhat important. Basically, because the bulk is constant negative curvature, all the sort of dynamics comes from just the boundary. And then a final comment, which is that, so if we're computing a partition function, we have to fix boundary conditions for the metric and the dilaton at infinity. So we've already said what we want to do with the metric. We want to consider geometries that have a length of the boundary which is proportional to beta. But we also need to fix the value of the dilaton at the boundary. If you look at the equations of motion for phi, it tends to grow towards a large radius. So what we're going to do is fix phi to be some 1, but at the boundary renormalized by some factor of epsilon. So phi diverges at the boundary, and we're going to fix this renormalized value.
Excuse me.
Mhm.
I might have missed this, but when you say it sets R equal to -2, you mean on shell, right?
On shell, but in a moment we'll say, actually I'll say this now. When we do the path integral, we're going to take a strategy where we integrate over phi first, and we're integrating phi over, we can define the model so that phi is integrated over the imaginary axis. Then this is like a delta function term in the action. So phi sets R equals -2 as a delta function.
Okay.
So it's even off shell, yeah.
Another question.
Mhm.
Boundary conditions. So here you are imposing Dirichlet boundary conditions, which is what you are doing GTK, right? But is there a clear interpretation or even how to study a model where you don't impose Dirichlet boundary conditions? You impose Dirichlet Neumann or Neumann.
Yeah, there's actually a paper about this somewhat recently by some postdocs at Stanford. I don't have a good understanding of it, but they talk about, they classify the different boundary conditions. They sort of talk about what each one might mean. Maybe I'll try to think about it. Maybe it's just called classifying boundary conditions in JT gravity. I don't remember the precise title. But yeah. Okay, so now that we have this action, let's talk about how do we compute the partition function z of beta in JT gravity. Eventually, we're going to use this to try to compute the spectral form factor. And also, the techniques for computing the partition function are going to be useful for computing all the space-time wormhole contributions that we'll eventually think about. So there's a lot of detail. What we're going to try to do is get an exact formula for z of beta. And so it's somewhat complicated and involved. And I'm not going to go over every single detail, but I'm going to try to highlight the sort of important points. Okay, so first, as I sort of just said, our strategy is going to be to integrate first over phi, the dilaton. And the upside of doing that is that the phi integral is like a delta function integral, setting r plus 2 equals 0 identically. So that means we're only integrating over metrics where which have this constant negative curvature, and those are just pieces of hyperbolic space. So when we consider this problem of the partition function, where we have this asymptotic boundary and we'd like to fill in the middle has to be filled out with just a piece of the hyperbolic disk. So here I have a picture of it. The hyperbolic disk is illustrated with this Escher, I guess these are fish or birds picture. There's a lot of volume out at the boundary, and here I've written the metric for this space and some coordinates. Rho is like the radius outwards, and you can see that there's a lot of space out near the boundary at large rho. And so the rules are for computing the partition function are that we integrate over geometries, which are pieces of this disk, where the boundary drawn in red has a length beta over epsilon, and the dilaton at the boundary. So we've integrated over the dilaton in the middle, but at the boundary it's fixed to be just 1 over epsilon. And then what we do is we're going to take epsilon to infinity, sorry, to 0. So this is our definition of the computation of the partition function in JT gravity. And so just a side comment, we can think about epsilon as the sort of cutoff radius for this piece of the disk.
Are you fixing the real part and integrating over the imaginary part of phi? Because you said the integral is over the imaginary axis, but on the boundary you are fixing it to real value.
Yeah.
Okay.
Yeah.
Okay.
So there's a number of approaches to doing this integral. So maybe I'll go back for a second and say, so what is the integral that we're doing? Well, the geometry in the middle is fixed. The only thing that we have that's different for our geometries is the shape of this boundary. So we can think about the path integral over metrics as the path integral over the shape of the boundary. And so there's a number of approaches to trying to do this integral. And I've listed a number here. And they all give the same answer, of course. I'm going to sort of talk about one method in particular that connects to what's called the Schwartzian theory, somewhat simply. And the Schwartzian theory is how this JT gravity connects to the SYK model, which is another toy model of holography that is approximately described by JT gravity. But I'm not going to really get into that. That's just a side comment. So one thing to keep in mind that's somewhat important is that our strategy is going to be to think about this boundary curve. We're gonna write the boundary curve in some coordinates. We're gonna parameterize it by sort of a rho of some parameter and a theta of some parameter. And we can think about integrating over this the boundary curve functions. And it's very important that we don't overcount, because let's say we take this boundary curve. This defines a geometry, and we shift the boundary curve up in this direction, or rotate it or something like that. Those give the same shape, the same piece of geometry, they just be parameterized differently in these rho and theta coordinates. So we don't want to overcount by integrating separately over different parameterizations of the same boundary curve. So that's just a little complication. So let's see. I'm not sure how much I've written more than I plan to actually talk about. I'm not sure how much detail to go into. Maybe I will not go too much into this slide. This is just saying we can parameterize the boundary in terms of some functions, theta of mu and rho of mu, or u, where u is, we can think of as the boundary time. So u is time along this boundary curve, and the total time has to be beta, beta over epsilon. And then in those coordinates, you can change coordinates to u and r, where r is something like the distance to the boundary. U again is this time along the boundary. And there's a nice way to write the metric and the extrinsic curvature of the boundary in terms of a function Schwartzian of u, which is this complicated function of theta of u. The JT gravity boundary action is like the dilaton at the boundary, which we fix to be 1 for normalized, times the curvature minus 1. So we just pick out this term here. And it turns out that you can rewrite this, the JT gravity action, the boundary term, as the integral of the Schwartzian derivative of this function of theta of mu in this limit where we take this renormalization parameter epsilon to 0. So what is this Schwartzian derivative? Well, I've written it here, but the important fact about it is that it's invariant under certain transformations to theta. It's invariant under SL2R transformations of theta of mu, which correspond to rotating this boundary curve or translating it in one of these two directions. So those two transformations of theta correspond to different parameterizations of the same piece of ADS2. So this action is going to be invariant under these reparameterizations of the boundary curve that keep the geometry the same. So that must have been true. We shouldn't have a different action for different parameterizations of the curve. And in fact, I think this Schwartzian action is somewhat unique. So it would have been reasonable to have guessed that the action should be something like proportional to the Schwartzian. I'll leave maybe as an exercise for interested people to look back at this slide and try to work out these facts about these boundary curves, which are true in the large cutoff limit. Okay, so now that we have what we've done is we parameterized our boundary curves by this function theta. We found an action as a function of theta, and then you can try to integrate over theta modulo these SL2R transformations of theta. So integrating over theta in general is hard. So we'll start by looking at the saddle point. The saddle point is very simple. It's just a circular boundary. It's parameterized by just a nice simple theta is proportional to u. And you can plug it into the Schwartzian action and find this action. So just going back, the saddle point is just a circle constant rho. But as I had said earlier, what we want to do is look at these very long times. We take beta to beta plus IT and take t to be very large. So in that case, we're going to really need to make sure that all the quantum fluctuations around the saddle point are controlled. And this Schwarzschild theory, I'll go back for a moment, is a complicated nonlinear theory. So the Schwarzschild as a function of this thing, we plug this tan of theta into this definition of the Schwarzschild, and it's very ugly in terms of theta. So you may think, how is there any hope of doing this path integral and getting an answer that we can compute? Well, this turns out that this Schwarzschild theory, this path integral over theta with the Schwarzschild action, is what's called one loop exact, which means the path integral is equal to the e to the minus action times the one loop determinant of the fluctuations, the quadratic fluctuations around the action, and that's it. There's no higher order Feynman diagrams around the saddle point. Everything cancels. So this was shown by Douglas Stanford and Edward Witten for the Schwarzschild theory, and I have my next slide just goes over sort of some of the key points behind why that's true. I'm not going to talk about it. I'll just leave that for anyone who's interested. But just to summarize, what this one loop exactness says is that z of beta, where we've integrated over all these geometries that are just pieces of this hyperbolic disk, is equal to e to the Euclidean action of the circular boundary. This term here, which comes from small fluctuations, the quadratic fluctuations around the circular boundary. And also we have this term here, which is e to the s naught. This comes from that topological term in the action, which is s. The action is s naught times the Euler character of the manifold. The disk has Euler character 1, so we have e to the 1 times s naught. So this is the exact answer for this partition function integrating over all these disk topologies. So from that partition function, you can do lots of things. You can look at thermodynamic properties or whatever. What we're going to do right now is we're going to say, what's the density of states that gives this partition function? So we take our function for z of beta that we had just found, and we say that it's equal to integral dE, some density of states rho naught of E times e to the minus beta E. And from that, you can just inverse Laplace transform and find this function here, rho of E. So
last question.
Yeah.
Does this technique that you're using here, is this unique to JT gravity, or does it work for any other model of dilaton gravity?
This technique of well, so one thing that's tricky about these other models of dilaton gravity, well, so JT gravity had this special fact that the curvature is constant and negative. So you don't have that, then it's sort of more difficult to study. And I don't really know if there's sort of other models of dilaton gravity that can be studied so like exactly.
The one loop exactness is not something you would expect in any other model.
Yeah, I think this is special. Yeah,
Okay.
maybe there's some other models that are related to JT gravity where this is true, but this is definitely this one loop exactness. Yeah, I should emphasize this is a very special thing in, like, say, higher dimensional gravity. We don't, in general, expect things like this to happen. So, and it's part of why JT gravity is a nice, simple toy model that we're going to be able to say lots about. So this density of states of JT gravity, some interesting features. So let's just look at first at high energies. High energies, the density of states goes as e to the 2 pi square root of 2e plus s naught. So just because the partition function was multiplied by this factor e to the s naught, this just comes along for the ride. And so this is supposed to be the entropy S of E. It looks like S naught, which is a large number, plus the square root of E at high energies. So for low energies, though, we look at this sinh of root E, and for small energies, we can just treat this as linear. So it looks like square root of E times e to the S naught at small energies. So the square root is actually somewhat reminiscent of the semicircle that we saw in the GUE random matrix theory. For the GUE, we found that the average density of states was the semicircle. And if you look at the edge of the semicircle, it behaves like a square root. So maybe you can try to draw real quick. The square root and the semicircle and this cinch thing would look pretty similar near the edge, and then they deviate at higher energies. So this fact that the JT gravity has this square root behavior near the edge, which turns out to be a hallmark of these random matrix theories, is going to be a key fact for our next lecture. So this disk gives a continuous density of states. It doesn't see that JT gravity has a discrete spectrum. So consequently, if we take this disk answer and we compute the spectral form factor, it gives a decaying slope. So the spectral form factor is z of beta plus it, z of beta minus it. We can take 2 copies of this answer we got for the disk, multiply them, and we find this thing here. So there's this one loop term. They combine for the 2 copies into this. This is 1 over square root of beta squared plus t squared cubed. And then there's this thing up here from the actions. And then it's all multiplied by e to the 2s naught. So this thing decays in time. And for a large time, it actually decays as a power of 1 over t to the 3/2 because of this term here. So it's a slow decay, but it nonetheless is a decay. So these 2 disks are not giving us the ramp or the plateau, and they're giving us a continuous density of states. So to understand how the ramp comes about, it's actually useful to think about this decay when it's coming from a little bit more physically. So we're going to look at this spectral form factor and think about it in a bit more of a Hilbert space picture. So let's start with this thermal field double state, which I've defined here. Thermal field double state is an entangled state of 2 systems, and it's labeled by inverse temperature beta. So here, if we have a system which we call left, and another copy of the system which we call right, the thermal field double is a nice entangled state where these are the energy eigenstates of the 2 copies of the system. And we've weighted this product of energy eigenstates by e to the minus beta over 2 times the energy. So one thing about this thermal field double state is that it's naturally computed, naturally related to computations in the path integral. So here I've drawn a little picture of what the path integral that computes the wave function of this state is. So let's say we're interested in this thermal field double state, the wave function in some basis phi left, phi right, where phi left and phi right are the values of the fields in the left copy of the system and the right copy of the system. So this thermal field double state turns out to be computed by this simple path integral, which is where you integrate over you have a path integral where Euclidean time runs from 0 to beta over 2, and the values of the fields at Euclidean time 0 are phi left, and the values of the fields at Euclidean time beta over 2 are phi right. So there's a nice simple path integral in the picture here. So here the circles sort of represent the spatial slices of the system, and this direction is Euclidean time. So this path integral on this Euclidean time interval computes this wave function. Another important property about this thermal field double state is that it has a nice symmetry, satisfies h left equals h right, so that it's invariant under translating in time in one direction on the left and the opposite direction on the right. So so far I've said I've defined abstractly this thermal field double state. I've said that it's nice in terms of the path integral. And then one other fact is that if we take the norm of this state and you work it out, you find that it's equal to z of beta, the partition function. And there's a nice path integral way of thinking about that. So we take 2 of these path integrals computing the thermal field double state wave functions, and we glue them together by integrating over the value of fields here and here. this just gives us a totally periodic path integral with Euclidean time periodic and beta, and that's the partition function. So this gluing of two thermal field double states to make the partition function, it's a simple picture in the path integral, and we're going to take advantage of that. So this thermal field double state plays a special role in gravity. We can think about this state as the state at time equals 0 of the two-sided eternal ADS black hole. So here I've drawn the Penrose diagram of the two-sided ADS Schwarzschild geometry. And I've drawn the time equals 0 slice in red. So the state on this slice is the thermal field double state. This is realized by Maldacena back in the 2000s. So in the path integral in gravity, we can prepare the state on this left slice. We can say what's the wave. We can prepare the wave function of this red slice by doing a path integral where we have an asymptotic boundary of length beta over 2, and we fix the geometry on some spatial slice that connects the two asymptotic boundaries left and right. So here, this red slice is supposed to be this spatial slice of thermal field double, and my claim is that if you fix the values of the fields on this red slice in this geometry, and you integrate over all things here with this asymptotic boundary length beta over 2, fixed values here, this gives the wave function on this for this black hole. So that's a bit abstract, but yeah.
Here you just have JT gravity, not actual Einstein gravity. So how do you know that this thermal field double state will have anything to do with a black hole?
Oh, so maybe I should be more clear. This statement about the thermal field double describing this two-sided black hole, this we believe to be true for in general in ADS CFT. So here the thermal field double is a state from two copies of the system. So we can think about this as two CFTs, one on the left and one on the right. And in the bulk using ADS CFT, we think that this thermal field double state is the state of a two-sided black hole connecting the left boundary and the right boundary.
Okay, I might have missed something, but when did we invoke ADS CFT? I thought we were just studying JT gravity.
So yeah, sorry, maybe I should be clear. So we were studying JT gravity up until this point. Now let's forget about JT gravity for a moment, and I'm going to tell you a general fact about ADS CFT.
Okay.
Which is that if you take this thermal field double state, where the two systems in the thermal field double state are two copies of this CFT in ADS CFT, the ADS CFT dictionary is telling us that the bulk description of that state is this two-sided ADS black hole. And so notice that here the two CFTs are not coupled. They're in an entangled state, however. And so the sort of the connectedness of this bulk geometry, the fact that the black hole has two sides, is related to the entanglement of this thermal field double state. And then furthermore, the wave function of this thermal field double state, I told you how to compute it sort of just generally in quantum mechanics using a path integral like this. But in gravity, the bulk state, its wave function can be computed using this sort of picture where the boundary has a length beta over 2, but we integrate over whatever's going on in the bulk here. So I'm going to tell you now how this does work specifically in JT gravity.
I have a question.
Oh, yeah. Mm-hmm.
So in the thermal field double, you've described some eigenstates of some Hamiltonian. I'm assuming this Hamiltonian is maximally chaotic.
Mm-hmm.
Okay, thank you.
Yeah, so we should think about these eigenstates as an example, you can take n equals 4 super Yang-Mills, and it's got eigenstates E, and we take two copies of n equals 4 super Yang-Mills, and we can make this thermal field double state for that for two copies of the system, and then in the bulk, it's dual to 2B string theory, and a state in that string theory is the state of this two-sided black hole, and the claim is that state is dual to the thermal field double of the n equals 4. super gang models. So in JT gravity, it's somewhat easy to deal with this wave function and the path integral which produces it. So first, we want to say, okay, so our goal is to say is to talk about the wave function of this two-sided black hole in JT gravity. So here I've drawn the Penrose diagram for the two-sided black hole in two-dimensional ADS gravity. And I haven't drawn a singularity. Maybe I should draw a singularity, but just to really, we don't really know if there's in JT gravity, there's not really a singularity because the metric is constant negative curvature. But just so to make things more familiar, I'll draw a fake singularity. So we want to talk about this state, the two-sided black hole time equals 0 state, which lives on a slice here, which I've drawn in red. And we want to describe that state in some basis. So we can calculate its wave function. So a nice wave function for JT gravity, a nice basis for JT gravity is states where we fix the metric along a slice of 0 extrinsic curvature. So the states of fixed metric, it's the metric on a line. The only diffeomorphism invariant property of that is just the overall length. So we can think of a basis of states in JT gravity as just the states with a spatial slice of length L, and the spatial slice has 0 extrinsic curvature. So then in this basis, we can calculate the wave function of the thermal field double state. It'll be a function of the length of this line here. And so as I comment, I've told you it has this spatial slice has length L, but it's going out from these two asymptotic boundaries. Really, we should be careful to regularize the length of this spatial slice. And there turns out to be a nice way to deal with that. And so we can easily talk about the renormalized length of this spatial slice. So this thermal field double state, we can talk about its wave function in this length basis. It'll be a function of the length. And the JT gravity version of the thing I said in the previous slide is that this wave function is computed by the path integral over geometries where there's a Euclidean boundary of length beta over 2. There's a geodesic, there's a 0 extrinsic curvature spatial slice of length L, or normalized length L between these two boundaries. And we integrate over all geometries in the middle here. So this is the path integral picture for this wave function. So one thing we're going to be interested in is what happens if we take this thermal field double state and evolve it with upwards in time on the left and upwards in time on the right. Let's say both by time t on the left and right. So here we take this thermal field double state on the time equals 0 slice. We evolve it to get a state on the purple slice, which is this state. And then let's ask about the wave function of this time evolved state in the length basis. So we can calculate this wave function again with a path integral. So here's a path integral which prepares the state on the red slice. This is a path integral over Euclidean geometries with this Euclidean time boundary. But then when we evolve in time, we integrate over Lorentzian geometries, which have time going upwards on the boundary. And then we integrate over these Lorentzian geometries up to a slice of length L on this purple slice. So this should give, maybe I'll write it explicitly, this thing should be equal to this thing here. So the behavior of this wave function is going to be important. So this two-sided black hole, we called it the connected part of the spatial slice of this two-sided black hole in Einstein-Rosen bridge. It goes from one asymptotic boundary to the other, and it goes through the horizon of the left black hole all the way to the other. So maybe I should look at this slice. So we can look at these spatial slices, the red and the purple. And we can see that the purple one goes, the horizon on the left is here, the horizon on the right is here. And so there's some distance in between the two horizons. And we can see that as we go up in time, we evolve the purple slice upwards, the length between these two boundaries should probably increase. So it turns out that the length of this Einstein-Rosen bridge, so the wormhole between these in this two-sided black hole, increases linearly in time. So if you just look at the classical ADS short-style geometry, you find the length of these zero extrinsic curvature slices grows linearly in time, and that's reflected in these wave functions, which we're computing as follows. So we can draw the time equals 0 wave function as a function of the length, like this, as some peak at some order 1 value of length. So that's here the length in between the two horizons is 0, but if you define the normalized length, you might have some sort of one leftover length corresponding to what's out here. As you evolve in time, the wave function is peaked around a larger and larger value of the length, and the value it's peaked around is proportional to the time you've evolved by. So the wave function on the purple slice, it's a function of L. It has small amplitude to have a short length, has a large amplitude to have a long length. So now let's get back to the spectral form factor. So if we take this time evolved state, this time evolved thermal field double state, and we take the overlap with the thermal field double at time 0, this turns out to be this analytically continued partition function, which we're interested in. So we can think about this using the path integral like this. So we can draw the path integral which prepares this time evolved state. It has a piece of Euclidean boundary of length beta over 2. It has some Lorentzian boundary. Here I've evolved only by t over 2. And we'll see why in a moment. So this creates the time evolved state on this purple slice. And then we take the overlap with the time equals 0 state by gluing together these two slices. So when we glue, we integrate over all these geometries with these boundary lengths. So there's a segment of beta over 2, t over 2, beta over 2, and t over 2. So altogether, that means the boundary has a length which has a piece that's Euclidean of length beta and a piece that's Lorentzian of length t. So that's precisely the path integral, which would give something like this. So this gives a physical picture of why this z of beta plus it decays in time. It decays in time because we're taking the overlap of this time evolved state, which has a long Einstein-Rosen bridge, with the t equals 0 state, which has a short Einstein-Rosen bridge. So basically, we're looking at the overlap of this red state and this purple state, and it's small as the purple state is evolved longer and longer in time.
I have a quick question.
Mm-hmm.
Does it matter that the Lorentzian and Euclidean time evolutions are interleaved? So you do half of one and then half the other?
Yeah, so this is a I unfortunately don't have time to talk about it too much, but it doesn't. So you could change you can think about this boundary as described by some contour and imaginary time. So you take the imaginary time plane it's got a real axis and an imaginary axis, and we're considering a periodic path in this plane, and different choices of periodic path correspond to different ways of segmenting up the boundary to Euclidean or Lorentzian or possibly complexified time. Turns out the answer is independent of how you choose this time curve. It only depends on the overall length.
So there are no poles you can deform with?
No, not in this case. Okay. You can think about it as it's because we're actually it's maybe it's important enough I should mention it. I'm gonna make a little new slide real quick. So what we're doing is we're looking at trace e to the minus beta plus it h. And to turn it, you can think about it as to turn it into a path integral. What you do is you partition this thing up into little bits. E to the epsilon h times, one way of doing it is thinking about this as a product of terms, e to the epsilon h beta plus it. And you take a bunch of these, say let epsilon is 1 over n, and we take a product of these up to n, and that'll give us this exponential here. We could also partition it up in different ways. We can think about this as a product of little epsilon h beta, where if you take a bunch of products of these, it'll make e to the minus beta h. And then times another piece, which is e to the minus epsilon h times it. So we can think about partitioning this exponential up into parts which are purely Euclidean evolution and purely Lorentzian evolution. And we get the path integral by inserting complete sets of states in between each of these little partitions. And because there's all these different ways of partitioning up the exponential, we can get different path integrals. But they're all going to give the same answer.
Very good. Thank you.
So finally, let's get back to we talked about z of beta plus it. Let's get back to the actual spectral form factor, just taking the modulus of that squared. So this is the probability. It's the probability of the thermofield double state to be time evolved and then return to the initial state. So we've seen that this disk contribution to z of beta should give a decaying answer to the spectral form factor. So they're not going to give the ramp and the plateau. But so these ramp and plateau, they're non-decaying. The ramp, in fact, increases as time goes up. The plateau stays constant. So what does this mean? This means that there has to be something in gravity that gives us a non-decaying probability for the thermofield double state, which likes to increase its length, to end back at a short length state. Furthermore, we expect that the answer for a fixed system is a noisy function, where maybe you average out to get the average ramp and plateau. So here, z of beta plus it, we expect to be a noisy function, and the noise should average to 0. But the spectral form factor, z of beta plus it, is the square of this noise. And we can think about it as having an average piece, which is the ramp, plus a different noisy piece, which averages to 0, just this noise squared minus the ramp. So in gravity, it's going to be really difficult to try to understand this noise. The noise will depend on the precise details of the energy levels of the system. And so it's tough to see something like that showing up in JD gravity with this very simple model. And in fact, we'll see that we don't find the noise. But we're going to find a ramp momentarily. And as we're going through this, I want you to keep in the back of your heads that this ramp here, it's something which shows up when we compute 2 copies of the spectral form factor. It doesn't show up when we compute 1 copy and then square it. So it's sort of something that shows up sort of intrinsically in this 2 copies of the system calculation, not in the square of the 1 copy thing. So that's sort of odd, but in gravity, it sort of has a natural interpretation.
Can I ask a question?
We'll see in a minute.
Maybe you're going to address it later in the case, just wait. I understand why the slope is generalizes to higher dimensions because because
this length growing always happens.
Yeah, the wormhole grows also in higher dimensions. But is the ramp and the plateau also something that we should expect in higher dimensions or in different theories of gravity, or is it something that is
Yeah,
with JT gravity?
so we expect them both in higher dimensional gravity. So for the ramp, we will give an explanation or a possible explanation for it in a moment that also works in higher dimensions. So yeah, I'll get back to that. But just for now, it's true that we do expect the ramp and plateau in JT gravity and higher dimensional gravity, because higher dimensional gravity is also chaotic and should have this random matrix level statistics. So just a quick side note, just about this decaying thing. So we're sort of looking for a ramp and plateau because of this random matrix universality. But even if you didn't have that, the spectral form factor can't decay forever if you have a finite dimensional Hilbert space or discrete spectrum. That's because if you just look at the time average of the spectral form factor over infinite time, if it decayed forever, the average over infinite time is 0, because for almost all the time it's decayed to 0. But if you just write out the spectral form factor in terms of just sum over discrete states, and you work out the time average, it's exponentially small compared to the spectral form factor. This had a sum over 2 energies. This has a sum over 1. Turns out this restricts the sum over energies from 2 to 1. So you find a small answer, but it's not 0. This is just a side comment to emphasize that even without this random matrix stuff, we'd still be expecting some sort of non-decaying thing in a spectral form factor. Okay, so now finally to the ramp. What we've done is we've looked at we've integrated over all these boundary curves. That sums up every contribution for the disk topology contribution to the spectral form factor. So it may be that JT gravity, it could have been that JT gravity just didn't have a ramp, in which case it would be sort of hard to understand in terms of discrete spectrum and quantum chaos. It turns out it does have a ramp, and to understand it, we have to look at other topologies because we've already exhausted the disk topology. So the ramp comes from, instead of having each asymptotic boundary be part of a disk, 2 decoupled disks, we consider all the geometries which are cylindrical topologically, where there's one asymptotic boundary here and another asymptotic boundary here, and they're connected by this cylinder. So this is sort of a natural candidate for the ramp because it appears when we have 2 copies of z of beta, not when we have 1 and then square it. So this is like the ramp, something that shows up when you consider 2 copies of the system. Also, the Euler character of this cylinder is 0. So in JT gravity, its topological weight is e to the s naught times 0. So that's like L to the 0, because L is the e to the entropy. And in random matrix theory, we found that the ramp is T over beta times L to the 0. It didn't come up with a factor of L. So the weight in terms of the entropy of the cylinder looks right. This fact that it only appears in the square looks good. So let's try to compute this this cylinder. And just as for some terminology, the cylinder is an example of what's called a space-time wormhole. Space-time wormhole connects distant regions of space-time. For example, even these 2 asymptotic boundaries are connected by this space-time wormhole. So we're not going to go in as much detail into this computation because some of the basic ideas are not so different from the disk computation. So first, I've just given you the metric for one of these cylindrical geometries that has constant negative curvature. Because remember, in JT gravity, we only integrate over geometries which have constant negative curvature. They're allowed to have this wiggly boundary, this wiggly cutoff boundary, but inside it has to be just constant negative curvature. So the cylinders, they have a parameter called b, and b is the length of a circular geodesic right in the middle of this cylinder. And here I've drawn, we can think about the cylinder as a quotient of the hyperbolic disk. If you cut along these orange lines, which are geodesics, and identify them, you get a cylinder. So under this identification, this geodesic here becomes this circular one here, and these wiggly boundaries out near the asymptotic boundary become the red thing and the purple thing. So as in the case of the disk, to include this contribution in JT gravity, this would be a contribution to z of beta times z of beta prime. We have to integrate over the shape of these boundary curves, the red and purple boundaries. We also have to integrate over b, the size of this circle. And there's a way to think about doing this integral, which will be useful for tomorrow, especially. It's also somewhat useful for what we're talking about now. We think of fixing the length b of this circle and cutting the geometry along this circle to cut it into two parts. So there's a piece with the red wiggly boundary, length beta, and it's a cylinder which also has this circular B boundary, which is a geodesic, zero extrinsic curvature. And then we have another one for this purple boundary. And then to look at the full contribution of all the cylinders, we integrate over the size of B and also the twist tau of how you twist the two, these are we'll call these trumpets. You twist the two trumpets relative to each other before gluing them. So it turns out that, and we'll maybe say some words about how to justify this tomorrow. This is the measure for integrating over this twist and the size B. The twist, you integrate from 0 to 2 pi B. So it's not you're not integrating 0 to 2 pi like an angle. You're integrating over the length you twist by, which is the length of this circle is 2 pi B. Or here I've defined B to be like the radius. And then you also integrate over B from 0 to infinity. So these functions here, if you compute the path integral for this, it's independent of this twist. So you can just integrate out the twist and you find a measure which is B dB, missing a factor of 2 pi, but whatever. And so you can think about, so yeah, just to summarize, you can think about integrating the cylinder as integrating over these two trumpets with the measure B dB. And then if you work it out, I won't go through it explicitly, you continue beta goes to beta plus or minus IT, you get precisely this ramp answer that we expected for sufficiently long times. It's a little bit more complicated at short times, but it quickly turns into just this nice formula. And so why do we get a linear function of t? The wormhole gives a natural answer, which is that it's the t ways to twist the boundaries relative to each other. So each asymptotic boundary will have a length which for large t goes as t, so beta is small compared to t. So we have a boundary of length t on the left, a boundary of length t on the right, and when we integrate over these wormholes, we integrate over the ways in which the left and right time are twisted relative to each other. And you can think of it as there's sort of t ways to twist the two boundaries. And that gives us this linear factor of t. So notice that this is pretty different than how we saw this linear factor of t in the random matrix theory case. That in that case, it came from this spectral rigidity, this 1 over delta E squared repulsion between eigenvalues that came from the van der Waals. So there, we thought about it in energy space, and it really told us about this repulsion between eigenvalues. Here, it doesn't. We found it in this neat way, working just in this spectral form factor, not in an energy quantity. This slide I'm going to skip. It's not very important. And so I'll briefly talk about the. Yeah.
So you just mentioned that this came from this repulsion of eigenvalues from the random matrix theory example that we talked about yesterday. And I was just curious, can you interpret this in a similar way, even though it didn't arise in that way? Here, like you said, the twist, but can we kind of come up with an interpretation that's similar to that for these two CFTs on each side of this?
Yeah, so maybe we'll talk about it a little bit more tomorrow, but basically, so we've calculated the spectral form factor. We can use that spectral form factor to do Laplace transform, Fourier transform to get what you would think is the pair correlation function of the densities. And this ramp would say that the pair correlation function has this piece, which is the 1 over e minus e prime squared. So this is telling us that these duals to JT gravity should have this eigenvalue repulsion, but it's not really telling us sort of, there's still some mysterious factors. We don't have a picture of sort of what are the things making up the discrete energies in JT gravity. We'll get to that a little bit more tomorrow.
Thank you.
Okay, so quickly, I'm going to give you an interpretation of sort of along the lines of what we talked about with the slope of why is the ramp growing in time. So these space-time wormholes, of which this cylinder is an example, we can think about them as processes involving the absorption and emission of closed baby universes. So in JT gravity, closed universes are circles. And we can think of a nice basis for closed universes as the closed universes that are circles of fixed length, zero extrinsic curvature. So let's label these states B, where B is the length of this closed universe. So these trumpet things that I've drawn, they look like path integrals where there's an external baby universe state, B. And so here I've drawn an example of another path integral with an external baby universe. This is the amplitude for one of our two-sided black holes of length L to evolve in time, end up at a two-sided black hole with length L prime, but also to have emitted a baby universe of size B. So if we integrate over all these geometries where we have these boundary conditions, we can interpret this quantity as this transition amplitude. So it's a transition amplitude between a black hole and a black hole plus a baby universe. And due to the topology, the cylindrical topology, this sort of process where we include a baby universe being emitted is exponentially suppressed, e to the minus s naught, relative to the contribution where we don't, which is just a disk topology. So there's a small amplitude to emit a closed universe. But we'll see that it has an important effect. Basically, it's this. So what we're doing is we're looking at this time-evolved thermal field double state. We've evolved for a long time so that its length on the purple slice likes to be very large. But what if we allow it to emit a baby universe of size B? Well, it turns out if B is of order T, so if the baby universe is very large, the purple slice has an amplitude to be small. So here I've drawn a little picture of sort of the picture. I've drawn a picture of what's sort of happening. Is you start out with a really long spatial slice, a long Einstein-Rosen bridge, and when the baby universe splits off, it can turn into a short baby universe with an order 1 length and a large baby universe of size T. So altogether, if you look at this process here, you create the thermal field double state, you evolve so that it gets really long, you emit a baby universe of size T, then the Einstein-Rosen bridge shortens, becomes short, and then you take the overlap with the thermal field double state. This overlap is now allowed to be non-decaying because this length is short and this length is short, so this gives a large overlap. The only thing that makes it small is the fact that this topology has changed. So it doesn't decay in time, but it's small because of the topology. So we're not in JT gravity, sort of the natural rules don't allow us to have these external baby universe things. So if we're calculating z of beta plus it, and we said we're allowed to emit a baby universe, we'd also have to specify its state, like what's its wave function in B, and that sort of isn't part of the computation of partition function. But what we are allowed to do is if we calculate z of beta plus it, z of beta minus it, we could have this system on the left emit a closed universe, which is then absorbed by the system on the right. So there's no external baby universe state. And then because this baby universe has size T, if we integrate over the different ways in which this baby universe can rotate while being traded, there's sort of T ways for it to rotate. That's related to this measure BdB for B. It's proportional to B, the size of the universe, which is T. So this cylinder, which gives the ramp, to summarize, the way in which it does it is that emitting this closed universe, which is large as a size T, is able to take away all the length of this long Einstein-Rosen bridge and bring it back to being like the time equals 0 Einstein-Rosen bridge.
So you have 5 minutes.
Oh, 5 minutes, cool. Okay, I'm just about done. Maybe I have 2 slides. Yeah. So
Perfect.
So I'll briefly talk about how this generalizes to higher dimensions. So the way in which we explain this plateau, let's say this ramp in the cylinder, in JT gravity, I use these sort of complicated geometries. I talked about these geometries that have piecewise Euclidean and Lorentzian parts, and I talked about these baby universes. And it's hard to deal with these sorts of geometries more generally. Another fact which I didn't really talk about is that the path integral over these geometries, it doesn't have a saddle point. So there's no classical solution. The reason is that the integral over B has a runaway direction towards small b. So B is proportional to T, but there's a constant multiplying T. And you can think about that constant as related to the overall energy of the system. But because we're in the canonical ensemble, we integrate over the energy with fixed temperature. So a way to solve that and make a JT gravity in the cylinder have a saddle point is to not consider Z of beta plus IT, but a different quantity, which is like a microcanonical version. You fix the energy instead of the temperature. It turns out in that case, the integral over B has a saddle point. So the whole integral over the cylinder has a saddle point. Two circular asymptotic boundaries and a B of size T that's set by, with a coefficient set by the energy. So this quantity, this Y, instead of Z, this is like, you can consider a microcanonical spectral form factor. It's a little bit better to generalize. And you can think about actually that the saddle point for this quantity, you're integrating over beta. Beta has a saddle point at 0. In the spectral form factors of the beta for the left, beta for the right, they're both equal to 0. So the geometries that give the saddle point have a purely Lorentzian time. So the cylindrical saddle points that give this fixed energy spectral form factor, they're cylinders with two periodic Lorentzian boundaries. So it's easy to generalize what happens in JT gravity to higher dimensions because there's this natural generalization of the geometry. So here I've drawn the Penrose diagram for the two-sided eternal black hole. There's a time translation symmetry where time goes up on the left and right on the up on the right and down on the left. And what we're going to do to construct the cylinder geometry is we're going to take a constant time slice, or here a constant time slice, evolve for some time t, find another slice, and then identify those two slices. That makes a cylindrical geometry with a sort of a singular cone tip, but the boundary has a length t. Now, in JT gravity, if you look at how the path integral works, it's natural to sort of deform this geometry in a complex direction near the tip of the cone. That actually makes this topologically cylindrical and non-singular. And that method turns out to easily generalize to higher dimensions so that this quote unquote cylindrical geometry, which is called the double cone, always exists. It's a piece of just the black hole geometry that we're familiar with, just this periodic piece. And it gives the ramp through these relative time translations of the two boundaries. And then just the last comment I'm going to make is that this ramp was telling us about these overlaps between a state which has evolved for a long amount of time, has a large length. It can have an overlap with a state of a short length. This has a sort of more conventional Hilbert space picture as follows. We started with the thermal field double state, and we evolved with a chaotic Hamiltonian. And we can think about that as roughly randomizing the state. So Z of beta plus IT is like the overlap of this randomized state with the initial state. Not quite a Haar random state if you know those words, but it's a quote unquote random state. And overlaps between random states in a large Hilbert space are typically small, but if the Hilbert space has finite dimension, the overlap is finite. So this fact that we're seeing that the ramp has to do with these overlaps of very different looking states, these non-perturbatively small overlaps of states, is related to this fact in sort of the boundary picture. Okay, so that's it. I'm just going to leave these questions up for tomorrow, because that's it for what I have to say today.
Thank you. All right, very good. Questions for Phil?
I have a
Go ahead.
verification pass. I might have missed something, but it seemed to me that in the double trumpet picture in JT gravity, you have two partition functions where each partition functions involves two boundaries, and so you have a total of 4 boundaries, right?
Oh,
While-
sorry. Let me go up to the picture just to make sure. This picture here. So each one has this boundary here. Is that what you mean?
Yeah, because later when you connected the two complex geometries, it seemed to me that you had a thermophile double on the left, a thermophile double on the right, and you were connected them through
I see what you mean. So maybe let me try to make sure I understand what you mean. So let's look at this picture. And so here I have a z of beta on the left and a z of beta on the right. But it's, if you sort of like try to think about cutting this, this is like the overlap of the thermophile double on the left with itself. And there's another thermophile double on the right. So each of these things is like a copy of the system. Is that sort of what you mean?
Yeah, and I think there was a picture later, a couple of slides down. Where
This picture.
Yeah, that picture.
Yeah.
So I was a little confused by this. Like here, you're considering actually 2 asymptotic boundary or 4 asymptotic boundaries.
So maybe it's a, I'm not sure if there's a bit of a terminology confusion, which is that in this quantity, this z of beta plus it, there's like one asymptotic boundary that's periodic, but we can slice it so that a slice has 2. So it's because the sort of boundaries, it's the same thing in that in this Hartle-Hawking, this thermophile double state. It's a state of 2 boundaries, but they're connected by the path integral via 1 boundary. So the special property of this thermophile double state that the boundaries, the boundaries are simply connected by this segment, even though when we slice, we can think about them as 2 copies of the system. Yeah, so
I'm having a slightly hard time to connect this to the picture you had later, or also before, where you actually have a wormhole. Like in Lorenz, you just have
this double
because I would expect, I would expect that to be the Lorentzian evolution of a slice of one of the 2 sides, not the whole picture above, right?
That's a good question. Yeah, so I don't think there's so this picture here. Okay, maybe let me say this. So what we've done is we worked at fixed energy, and then the saddle point is at beta equals 0. So we can try to do that to this picture, and let's see what happens. So beta is like the length of this segment here and the length of this segment here. So what's sort of going on is you can think of this, well, I'll say first, so first there's that. And the second thing is that in the middle of this geometry here, it's a complex or Euclidean geometry. So what we do when we consider this fixed energy thing is we're going to send the length of this segment and the length of this segment, also these ones, to 0, so that these 2 things are now touching, these 2 points. These 2 points are now touching. So it's sort of like not a natural thing to do in this point of view of the geometry. So it's a little confusing to interpret, but you could instead think about first. So yeah, I think it's confusing, and I don't have a good picture of how to connect this Lorentzian double cone to this complexified picture of the baby universes, except for that, in general, it's actually more natural to consider in some ways a version of this double cone, which is complexified in the bulk here. And it's a little bit complicated. I don't have time to go into much detail, but let's say, here's a quick way to say it, is that as we're going inwards, this is decreasing R. And what we want to think about is metrics that are related to this, just by a change of coordinates, where we take R to be complex as we go near R equals 0. And if we complexify R, we get a metric which is not Lorentzian. It's now a complex metric. But instead of this cone tip thing here, we have something that's more like this B circle here. So the by complexifying these metrics just using complex coordinates, you can sort of go back and forth between these two pictures. But the question you were asking specifically about how to think about slicing this thing so that there's sort of a thermal field double here and a thermal field double here. Yeah, I'm not sure. I don't have a particularly good picture about this fixed energy version of that, besides saying start with the fixed temperature version and then fix the energy. There's a picture for the fixed temperature, and then you can fix the energy.
Perfect. That's clear. Thank you.
So actually, sorry, maybe I'll just make one last comment about it, which is that like, so we've prepared this state on this slice with a path integral of length beta. And when we fix the energy, you can think about just forgetting about this path integral preparation state. You just have a black hole of some energy and you evolve in time and then take the overlap with the black hole with that energy. So there's like a physical picture of just evolving a black hole, fixed energy instead of fixed temperature. And you can have the same closed universe thing happening. Yeah.
Actually, let me ask a follow-up to that. When you say that you start complexifying the metric when you go in R, is there some finite R where that happens? The imaginary part is sort of 0 and then it picks up some value at some finite R?
Yeah, you're free to choose different contours. So like, let's say we consider the complex R plane. There's R equals 0 is this singular cone point. And you want R to go to plus to the real axis at infinity so that the boundary conditions are satisfied. But so in between, in the R is minus infinity and infinity, you're allowed to go between those through any contour that doesn't hit the R equals 0 point. So it can deviate away from being real anywhere along the way. And the answer you get is sort of,
and computationally, it's convenient to choose a kinky contour.
yeah, computationally it is. Yeah.
Okay, great, thanks. So Christian?
So my question is, I'm just sort of trying to think about like this in terms of thermalization of a perturbation to a black hole horizon. And I guess the way that I'm thinking about it is that if you consider the thermal 2-point function in the Heisenberg picture, you can sort of write it down in such a way that you sort of get the spectral form factor, at least that sort of phase combination that you use.
Yeah.
And then you sort of strip off the matrix elements. And then that more or less is the spectral form factor. So in some sense, I sort of see that as like describing the thermalization behavior of the black hole horizon after it's perturbed.
Yeah.
So what does a ramp and plateau mean for the actual like thermalization horizon?
Okay, so first I'll talk about, okay, to connect to what I was saying a little bit more simply, let me tell you first this. So the thermal 2-point function that you're asking about, it's neatly related by like analytic continuation. I'm just going to scroll down to a free page so the 2-point function. I'm going to draw a picture in the Penrose diagram of that 2-point function. You have an operator here and you have an operator here. This is related by analytic continuation to a 2-point function where you put one of the operators on the left-hand side. So they're separated in time by a time t. These are separated by time t, and here they're separated on the left, and the left and right ones are separated by time t and on opposite boundaries. These are just related by t goes to t plus I beta over 2 in this 2-point function. So they're related, but they're physically different. So the first thing I'll do is tell you about how this thing works, and then I'll tell you about how this thing works. This is a bit more simple to connect to what I was saying today. So the reason this thing decays, this thing also decays in a very similar way. And the reason is that this 2-point function is sort of measuring the distance between these two operators. Like the propagator in this geometry, O on left, O on the right, is sort of like e to the minus the mass times the geodesic distance between the two. And we've seen is that we evolve in time. The geodesic distance between these two things grows. So this propagator decays. Then this thing I said about the wormhole, we can take that into account, which is that in this 2-point function, we ask about what's happening to the 2-point function as we evolve forwards in time. The length of the wormhole between the two sides grows, but then it can shorten. It can shrink back to a short size by emitting one of these baby universes. So there's a picture along the lines of that. I wrote a paper about this. If you're interested in more, there's that's sort of how it works for this two-sided 2-point function. Now, to go back to this picture, it turns out, maybe I'll say there's a second way to think about this. Basically, when you consider these wormhole geometries, the sort of physical interpretation is a bit murky because of basically diffeomorphism invariance lets you move around the wormholes in a lot of ways, so that sort of one gauge fixed choice of where to put the wormholes gives you one physical picture. A different way gives you a different physical picture. So the thing I just described is one physical picture. Another physical picture is that this right-hand side creates a particle, and it's able to, a wormhole creates a little shortcut between the two boundaries. And so the particle is near here through this wormhole, even though the Einstein-Rosen bridge is small. So in this 2-point function, the first picture is a little bit unclear, this shortening of the wormhole. But this second picture, in terms of the wormhole creating a little shortcut in the space-time, is more clear. So basically, you throw a particle in the black hole, it would like to thermalize, it would like to go into the black hole and be gone forever. But a wormhole can appear which links that particle that you've thrown in out to the boundary again. So that's why it doesn't decay.
So in that sense, could you sort of think of the horizon as sort of like this collection of wormholes?
I'm not really sure. So it's like the wormholes have a very small amplitude to appear. So the way I think about it is like, I'm not really sure if there's a way to think about it that way. Yeah. So the one thing I would say is that in the computation, you only use sort of one wormhole to find this ramp. It's not clear if there's a way to think about what's going on in terms of many wormholes.
Okay.
Maybe that's more related to the plateau, which we'll talk about tomorrow.
So just a quick follow-up question. So in Maldaceno's original paper, he was talking about the issue of the 2-point function just decaying to 0 if we just think about it in terms of quasi-normal modes in a semi-classical background. And he essentially talked about this, you have to include the black hole saddle point and also the thermal ADS saddle point. So is this thermal ADS saddle point sort of related to this baby universe?
It's actually completely unrelated. So there's two things I can say about it. One is in JT gravity, there is no thermal ADS, so it can't sort of help. The second is that the thermal ADS doesn't give you sort of the right behavior. It gives you something that it oscillates instead of decaying, but it doesn't have the right size and it doesn't have the right sort of noisy behavior. So in higher dimensions, we expect that there's this wormhole effect, but there's also the thermal ADS effect. The thermal ADS effect is not related to this random matrix theory stuff. And you can make it small compared to the, you can make it not, it's not the right side. You can make it like, yeah. Basically, it's easy to separate the wormhole out from this thermal ADS effect.
Okay, thank you.
Great. Any other questions? Okay, so maybe it's a great time to stop the recording.